Assalamualaikum to one and all. It's great to have you back to Sir Caleb's Physics and Chemistry tutorials for high school learners. In today's episode, we go back to some basic applications of Newton's second law of motion with emphasis on computing the net force or the acceleration of a body using the law of acceleration and kinematics equations on uniformly accelerated motion. So just stick around, watch and learn. Here are the questions. Number 1. Two people are pushing a stalled car. The mass of the car is 1,850 kilograms. One person applies a force of 275 Newton to the car, while the other applies a force of 395 newtons. Both forces act in the same direction. A third force of 560 newtons also acts on the car, but in a direction opposite to that in the people are pushing. The force arises because of friction and the extent to which the pavement opposes the motion of the tires. Find the acceleration of the car. Question number 2. A 1,580 kilogram car is traveling with a speed of 15.0 meters per second. What is the magnitude of the horizontal net force that is required to bring the car to a halt in a distance of 50.0 meters? And question number 3. A person with a black belt in karate has a fist that has a mass of 0.70 kilogram. Starting from rest, this fist attains a velocity of 8.0 meters per second in 0.15 seconds. What is the magnitude of the average net force applied to the fist to achieve this level of performance? For our first question, we are given the mass of a stalled car equal to 1,850 kilograms. So in our vector diagram, the car is represented by a particle. And the two people are exerting the forces F1 equals 275 newtons and F2 equals 395 newtons. Right? So both F1 and F2 are directed in the same direction. And there is an opposing force, F3. This is due to the friction between the tires of the car and the pavement. All right. So the amount of frictional force is equal to 560 newtons. Take note there is a negative sign to emphasize that the force of friction is opposite to the direction of F1 and F2. And our target variable is the acceleration of the car. We denote that here as A. But before we can compute the acceleration of the car, okay, we need to first determine the net force. All right? The net force that's causing this acceleration. So the net force on the car is just the vector sum of the three forces, F1, F2, and F3. That is, Fnet equals 275 newtons plus 395 newtons plus negative 560 newtons. So when we do our addition, we get the net force on the car equal to positive 110 newtons. Alright? The positive sign of the net force simply suggests that the net force has the same direction as F1 and F2. Right? So, we can now calculate for the acceleration of the car using the formula of Newton's second law. That is, A equals Fnet divided by the mass m. That is 110 newtons, which is our computed net force, divided by the given mass of the car, 1,850 kilograms. So, we get the acceleration of the car equal to positive 0.059 meters per second squared in two significant figures. Alright, so as expected, based on the second law of Newton, the acceleration is also positive because it should have the same direction as the net force. Moving on to question number 2. We are given the mass of the car, all right, 1.58 times 10 to the third kilogram. It is traveling with an initial speed v naught equal to 15.0 meters per second, right? It decelerates or slows down uniformly until it comes to rest, right? Through a distance equal to 50.0 meters. So the final velocity or speed of the car is 0 or 0 meters per second. All right, take note, the final speed of the car, okay, is 0 because it comes to rest after traveling a distance of 50.0 meters. All right, so we are asked to find the net force, all right, that is uh, causing the car to decelerate. All right, this net force is necessary to bring the car to a full stop after it has moved a distance of 50.0 meters. In the diagram, we indicate this net force as being directed opposite to the motion of the car. All right? Now, you might be asking, where is this net force coming from? Well, this net force arises as a result of the car driver applying the brakes. Hence, it produces the retarding force coming from the surface of the road, or simply we call it the force of friction between the car's tires and the rough road. Right? So again, we make use of Newton's second law of motion in order to find the net force. But before that, we need to compute first the acceleration. Alright? So this time, the acceleration is determined using a kinematics formula. That is, acceleration equals quantity v squared. This is the final speed minus v naught squared. That's the initial speed all over twice the distance. Right? So when we substitute or plug in the given data to this formula, we find the acceleration equals 0 that is the final speed, minus, all right, the square of the initial speed v naught, 15.0 meters per second. And then, after squaring v naught, we divide it by 2 times 50.0 meters. So again, when we do our math, we get the value of the acceleration A equals negative 2.25 meters per second squared. As expected, it has a negative sign because this acceleration, all right, commonly called deceleration, okay, meaning that the car is slowing down. So it is directed opposite to the motion of the car, all right, just like the direction of the net force. So we can now compute the net force that caused this car's acceleration, again using Newton's second law. Fnet equals ma, or Fnet equals 1.58 times 10 to the third kilogram multiplied by the computed acceleration, negative 2.25 meters per second squared. So if you do your math, we will get the value of the net force equals negative 3.56 times 10 to the third power Newton in three significant figures. So just like the acceleration, the net force also has a negative sign, meaning it is directed opposite to the motion of the car. Last but not the least, we have the following given data for our last question, number 3. The mass of the karate black belter's fist is 0.70 kilogram. It is initially at rest, so V naught is equal to 0. And upon delivering a punch, it acquires a final speed V equals 8.0 meters per second. Right? In just a split of a second, that is t equals 0.15 seconds. So we are asked to compute the magnitude of the average net force applied to the fish to achieve this level of performance. So again, we first find the acceleration. All right. This time, we are using the formula A is equal to final velocity minus initial velocity divided by the time. But since the initial velocity is 0, so we only have A equals the final velocity divided by the time t. That is, A equals 8.0 meters per second divided by 0.15 seconds. And we get the acceleration of the fist equal to 53 meters per second squared. Now, this high acceleration is produced by a net force, all right, equal to the product of the mass of the fist, all right, which is given as 0.70 kilogram. And when multiplied to the computed acceleration, 53 meters per second squared, we get, all right, the amount of the net force necessary. That is 37 newtons, all right, in two significant figures. So this is the magnitude of the net force necessary to achieve such level of performance. All right? When you're hit by this karate punch, it is like being hit on the head by a 1 kilogram brick falling, all right, at 3.8. The acceleration due to gravity, or 3.8 g. That is how much it can uh, give a pain when you are hit by such a karate punch amounting to 37 newtons. So that's it. We are done. Till the next episode, mabuhay. Mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.